Today, we're going to start Math 110A content. We start with Chapter 2, the limits and derivative. And in 2.1, we're going to talk about the tangent and velocity problems. First, we're going to talk about the tangent problem. The word tangent is derived from the Latin word tangens, which means touching. So a tangent to a curve is a line that touches the curve. In other words, a tangent line should have the same direction as the curve at the point of contact. But how can this idea be made precise? For a circle, we could simply follow Euclid and say that a tangent is a line that intersects the circle once and only once. However, for more complicated curves, such as this one, this definition is inadequate. So over here, we have a curve C with two lines, L and T. Now, this line L intersects the curve only once, but it certainly does not look like what we think of a tangent. So the line T, on the other hand, looks like a tangent, but it intersects the curve C twice, here and over here. So to be specific, let's look at the following example. In this example, we're trying to find the equation of the tangent line to this parabola at this point 1, 1. So here's a parabola for y equal to x squared, and here's a point 1, 1. We need to find the equation of this tangent line that passing this point 1, 1 on this parabola. We have one point on this tangent line that was given. However, we don't know the slope for this tangent line. In order to write the equation, we need the slope for this tangent line. So how do we do that? So how do we find the slope for this tangent line over here? Okay, now let's take a look at this diagram here. Okay, so this is a point P, and we're trying to find the slope for this tangent line. Okay, now what we do here is near this point P, we're going to pick a point Q, which is on the parabola, but is closer to this point P. Okay, and then we can draw a line that goes through this 2 points, PQ, and that's called a secant line, okay, secant line PQ. What happened over here is, if you move this Q closer and closer to P, like for example, if we move it here, and that's the secant line, and if you move it even closer, and that's the secant line, as you can see that as Q moves closer to P, and what happened here is this blue secant line over here is getting closer and closer to this tangent line over here, okay? You don't have to choose this point Q to be on the right side of this P. So let's choose this Q to be on the left side of this P, okay? On this side of this parabola. So what happened here is you draw this secant line PQ again, and then you move this Q closer and closer to P. And as you notice that what happened here is the secant line PQ is getting closer and closer to this red tangent line over here. So that will give us an idea if we can calculate the slope for the secant line PQ, and then move this Q closer and closer to P and see what happened to the slope. Is the slope approaching to a certain number? If the slope approaching to a certain number, then that slope will be the slope for this tangent line over there, okay? So that's the idea, okay? So over here, we get this point P 1, 1, and we pick a nearby point Q on this parabola. Now, because the x coordinate is denoted by x, this point is on the parabola. So to satisfy this equation, y equal to x squared, so the y coordinate will be x squared, okay? So this is the coordinate for this point. Now, we can calculate the slope for this secant line PQ by using the slope formula, okay? So we have x squared minus 1 over x minus 1, okay, right here. Now, you can simplify and reduce this, okay? Now, we can factor this x squared minus 1. This is the difference of 2 squared. So we can factor that into x minus 1 times x plus 1. And then the x minus 1 here, the x minus 1 is a common factor. You can divide them out, okay? So finally, you will get x plus 1. So the slope for this secant line PQ is actually equal to x plus 1, with the x here being the x coordinate for this point Q. So let's make a table. So this is a table, and I'm going to pick the x coordinate to be 2. So this x coordinate is 1, that's 2. And then I'm going to move this point closer to P. So I move the x coordinate to be 1.5. And then later move the x coordinate to be 1.1, and then 1.01, and then 1.001. Okay, so move it closer and closer to 1, and approaching this 1 from the right side. Okay, so, and then we'll calculate the slope for the secant line over here. Now, as you can see that the slope for the secant line here is just x plus 1. So I add 1 to that. So that's the slope for the secant line, that's 3. And add 1 to this is 2.5, etc. Okay. Now, what do you observe over here? As this x getting closer and closer to 1, okay, approaching 1, closer and closer to 1, okay, what happened to this slope for the secant line PQ? Take a guess. Okay, it's going to approach to 2, right? Getting closer and closer to 2. You can do this also by picking the Q on this left side of this point P. Okay, so what happened here is I choose the Q over here with x coordinate to be 0, and then later on choose a Q over here with x coordinate to be 0.5, and then x coordinate to be 0.9, 0.99, 0.999. Okay, so on the left side of this P, but getting closer and closer to P. Now what happened here when x is closer to 1, okay, closer to 1, or we say approach to 1. And what happened to the slope for the secant line, okay, PQ? Looking at the pattern, it looks like that is approaching to 2, right? Okay, so approaching to 2. So this suggests that the slope for the tangent line should be m equal to 2, okay? So we say that the slope for the tangent line, so the slope for the tangent line, okay, is the limit of the slope of the secant lines, okay? So you take the limit of those slope for the secant line, and that's the slope for the tangent line over here, okay? So to express this, you use this notation. And how do you read this? You say the limit of the slope for the secant line PQ as the Q getting closer and closer to P along the curve is equal to the slope for the tangent line M. And since the expression for the slope for the secant line PQ is equal to x equal to this, so we say the limit of that is equal to 2. The slope for the tangent line is equal to 2. Okay. Now after that, so if the tangent line has slope equal to 2, we can use a point slope form to write the equation for the tangent line. Okay. So the point slope form is y minus y1 equal to m times x minus x1. So now the point that we have for this tangent line, we know that passing 1, 1. So the point we have here is 1, 1. So using the point slope form, we have y minus 1 equal to 2 times x minus 1. And when you isolate y, then we get y equal to 2x minus 1. And that's the equation for the tangent line. And this is called slope-intercept form because this is the slope and this is the y-intercept.